Okay, so we have all the definitions necessary. Now we can formulate the principle of least action, okay? But before we do that, any questions?
No, sir.
So suppose that, we are trying to figure out what the trajectory of a physical particle is given the boundary condition that at t equals to 0, it's at x0, and at t equals to f, it's at xf. So here's the problem. Along the y-axis, we have the position of the particle. Along the x-axis, we have time. And suppose we start at time t0 and finish at time tf. And we are told that at time t0, the particle's initial position is x0. And at time tf, the particle's final position is xf. So on a space-time diagram, this is what it looks like. So these are the boundary conditions. Now, the particle can take all sorts of paths, right? It can go towards xf, it can turn back, go towards xf, turn back, like this. Or it can do it more straightforwardly, right? So it can have all these kind of different paths, right? All of these pink lines are a different path. So each of these paths, x of t, is a path, but each path, obeys the boundary conditions that x at t0 is x0 and x at tf is x of f. Okay. Now note that for each of these paths, we can calculate the action, right? We can do the integral for each of these functions, and we will get a value for our function. Now, what the principle of least action says is that for the physical path, so of all these paths, there would be one path which would be physical. Suppose it's this path, the red path. Okay. So for the physical path, the action will be stationary. So what does this mean? It means that if you change your physical path a tiny bit, so you take your physical path and you change it infinitesimally. Okay. So you change it infinitesimally. So this is your physical path, and you're changing the path ever so slightly. So then, of course, your action would change in principle, right? But the principle of least action is saying is that, when you do, change the physical path to a neighboring path, the change in the action is 0. Okay? This is what it means for the action to be stationary. And this is what it means for the action to be, this is called the principle of least action. Okay? Why is it least? Because suppose I draw this picture in a different way. So what I do is that I use the XY plane. So this is the x-axis, this is the time axis, and this is the x-axis. This is the initial position, and this is the final position. And you have all these paths going. But there's one path, which is the physical path. And along the z-axis, I'm going to plot the action. If I plot the action, then the principle of least action is saying is that the action will have some arbitrary form, but it'll have a minima right on the physical path. Okay? So that if you now change from this physical path a tiny amount, this will not change. Okay? So this is what it means for the action to be to be stationary. Okay? So whereas if you follow one of the non-physical paths, say this one, and you vary it a little bit, then in this space it goes somewhere like this. If you change, you're changing the action quite a bit. Okay? For if you change the green path slightly, the change in the action will not be 0. Okay? Is this clear what I'm trying to say?
Yes, I think I got it.
Yeah, I mean, this is it's a very subtle and, in a sense, a very deep concept. But, it's something we all, we'll flesh it out. The stationary, nature of the path is extremely important when we're doing path integrals. Okay, we'll see. All right. So I'm going to do something quickly. I'm going to change now that my electricity is back, I'm going to change to the Wi-Fi and put my phone on charger for future. So just 1 second, okay? Are you guys still there?
Yes, sir.
Okay. All right. So next, what we want to do is we want to formulate this principle of least action mathematically. So let's introduce the notion of the variation of a path. So the variation of a path, remember that the path is a function of t. So the variation of the path, delta x of t, is another path which is close to the first path minus the original path. Okay, so this is this is by definition small, infinitesimal. And so this is our original path. This is the slightly varied path. But we subject to so we are going to do variation subject to the condition, to the boundary condition that at t0 and at tf, the variations vanish, okay? So we're going to assume that. Okay. Now, So once we have chosen a particular path, doesn't have to be physical. Once we have chosen this gives a particular value of the action S. But when we vary this path, the action itself will also vary. So under the variation, where xt goes to xt plus delta of xt, what happens is that S itself will change to S plus some small amount delta S. This delta S is called the variation of the action. Okay. And then the principle of least action says that for the physical path, xt, the variation of the action is 0. As simple as that. Okay. So, I'll make some comments, and then perhaps we can take some questions. And the comments are, like Newton's law, the principle, this principle, is a fundamental assumption about the universe, or about physical systems. Neither can be derived. Neither can be derived from some deeper principle. Okay. It is the way it is. Okay. However, this principle is equivalent to Newton's law. Okay. And number 3 is that the principle of least action is a minimization / maximization or extremization principle of which kind mathematics is full of. So this was a very convoluted sentence. So for example, if I ask you, what is the shape of a surface, with minimum area, that bounds a given volume. What would you answer?
Sphere.
Right. So, but it could have been this same volume here. It's this. It's this. But we are saying that the surface area has to be minimum. And it turns out this is the correct answer. So this is very similar to the principle of least action, because we are minimizing, a functional. So we are minimizing a functional. In this case, the functional is the area of a surface, which yields a particular function out of infinite number of functions. Which is the sphere. Okay, so this is exactly the same analogous thing. Okay, so these are my comments before we go into deriving a differential equation that the path has to satisfy, which is equivalent to Newton's equation. Let me see if you have any questions. Any questions?
I don't, but I think Nahi commented something.
Okay, where did you comment, Nahi? I have limited visibility at this point.
The Google Meet, I think. I can't see it either properly since it's my phone, so.
Okay, no, I can see it now, okay. Maybe the question is a bit stupid, but I am a bit confused about it. Can anything be said about the uniqueness of the physical path? What if there is more than one path that extremizes the action? The boundary conditions would preclude it. Okay?
Okay, sir.
Yeah. Yeah, I don't think there can be more than one. But let me also think about it, because is there a physical situation where, given the same boundary conditions, two different things can happen? One of two different things can happen? I don't think so.